So electron dots means I'm going to put the elemental symbol and use dots to show the valence electrons. Nitrogen is the fifth element from the left in its row. The fifth element from the left in its row on the periodic table. So I need 5 dots. 1, 2, 3, 4. I'm putting 1 dot on each of the 4 sides as if there were an imaginary square there. And then I can pair up 1 more on any of those 4 sides that I want to in order to get to those 5 that I need. You need to know that nitrogen needs to have 8 electrons to have a full valence level and be more stable. Chlorine is the 5th element from the left on the periodic table. And when we get the larger elements, you actually skip over the transition elements to get that number. I'm sorry, the 7th element from the left. So I put 1, 2, 3, 4, 5, 6, 7 in the same way. So that's the electron dot notation. What I can do now is to share electrons. By sharing this electron here and here, chlorine has 1 more than it had before. It now has 8 electrons, so it has a full valence level. The nitrogen only has 6 at the moment. So I can keep adding chlorines in this manner, so that now this chlorine has 8, nitrogen has 7, 1 more chlorine, and now both the nitrogen and all the chlorines have 8 electrons, so they have a full valence level. They are more stable. That gives you the best ratio. This is now electron dot notation. And the rate.
You did 3 chlorines, then it's supposed to be 2 chlorines and 2 nitrogen.
So what we need for a product formula is NCl3 using electron dot notation and sharing arrangements. Okay? Now that we have what the product is supposed to be, we can balance the equation using coefficients. We haven't done that yet. All right? Now, if the product is a liquid, I'm adding to the problem now. If the product is a liquid, you want to determine the physical states of the reactants and balance the equation. Okay? So what physical state do I assign to this? It is a gas. We just went through that. I told you that certain elements, when they're by themselves and unbonded to anything else, well, this is bonded to itself, not to something else. So this is one of those elements that I mentioned earlier that's going to be a diatomic gas. Okay? This also is one of those 11 elements that I said would be a gas, and one of the 5 that I said would be a diatomic gas. Okay? Now we're ready to balance the overall equation. So we have nitrogen and chlorine. That's all we have to worry about here. Now I've kind of moved this over. Normally I put it up under the equation itself. You have to know that we're talking about splitting it up along there. So we've got 2 nitrogens and 2 chlorines on the left side, 1 nitrogen and 3 chlorines on the right side. We balance the formulas. Now we can't touch this. Okay, we can't touch the subscripts. Got to leave the subscripts alone. All we can do is put coefficients in front of the symbols out here to get a balanced equation. So, starting with nitrogen, I have 2 on the left side here and only 1 on the right. Using coefficients to get 2 nitrogens, I'll put a coefficient of 2 in front of that species. Oh, by the way, I said this was a liquid too. Right here, I need to put L there. So now I have 2 nitrogens on the right side. But I also have 2 times 3 or 6 chlorines, because that coefficient 2 Applies to everything in that formula.
Add three.
Hmm?
What do you add three?
Now we've got to go back on the other side. Yes, we want to go back on the other side and show that in order to get this chlorine up to that same number, 6, I need a 3 here. So that'll give me 6 chlorines and the equation's balanced.
What I was asking earlier about the sharing.
Mm-hmm.
So you could, like, I mean, I did that, but I was just wondering, like, if you could put chlorine in the middle and then do nitrogen around it.
I don't think you'd ever get it properly put together if you did that. You could, but the problem is that if you put chlorine in the middle, start putting nitrogens around it, it's never going to work out. And you weren't here in the class when we went through all this, but basically when you do this process, if one way you're trying to do it doesn't work, throw it out and start in a different way. Okay? Yes?
Where y'all get this third chlorine from?
Well, actually, overall, there are 6 chlorines.
You have to make
I'm talking about when you get it in.
I'm talking about the sharing stuff.
Okay? Nitrogen, because nitrogen had 5 valence electrons. And the only way for it to share with chlorine in a way that gives both the nitrogen and chlorine 8 valence electrons is using this process. Okay?
Did you double bond somehow?
Well, you could, but you don't do that unless I tell you that it's that you want to go that direction, okay? Chlorine, the problem with double bonding here is it would require you to do something called expanding the octet, and I didn't teach you that in this class, okay? Because chlorine already has 7 electrons. If you double bond, that's going to give it what? 9, okay? You can't double bond with chlorine. You can triple bond with it, but that's expanding the octet, and I haven't taught you that in this class. Okay? Any questions about that? All right, then let's talk about determining physical states. All right, we started out the class talking about 11 gases whose physical state are 11 elements whose physical state will be a gas as long as they're not bonded to anything else. We're not talking about themselves now. They can be bonded themselves and still be a gas. But as long as they're not bonded to anything else, they will be a gas. Yes?
I was fixing to ask, when you use the electron dot in the sharing arrangement for all of them, but I just thought about all of them, and when you put them together, they'd be polyatomic and stuff. Is this for synthesis reaction?
Well, I just asked you to do it in this particular case. Usually, this sharing of electrons, we typically only use this for covalent bonding. Sharing of electrons happens with covalent bonding. If we were doing some kind of ionic bonding, you could use the electron dots, but then you draw arrows to show where the electrons are leaving and going somewhere else. In ionic bonding, the electrons actually leave one element and go to another. Or one, well, it can get more complex. That's all we've done in here. Okay? All right. If I put this stuff in water, what would be its physical state? If I put this stuff in water, what would be its physical state? Please write it down on your paper. What would be its physical state if I put this stuff in water?
That's a different
By the way, stuff is a biblical word too. What?
So you're starting a whole different one.
Yeah. 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 It's in the Old Testament. Everybody got it? What kind of a substance is this?
That's a transition metal.
It's a transition metal or transition metal, okay? Have you ever heard of any metals that dissolve in water? No. Metals don't dissolve in water, so it's a solid. Except for mercury, all metals will be solids at room temperature and pressure. Okay? That's pretty simple, right? Okay. How about if I do this? Determine the physical state of this substance. Determine the physical state of this substance. So, what kind of a substance is this? Okay. Can you classify it any other way other than a solid?
It's insoluble.
Huh?
Milk.
You think it's a gas? Okay.
It's insoluble.
How about ionic? Can we classify it as ionic? Because there's a polyatomic ion there. Okay? Since this is ionic, we want to know if it's going to be aqueous or not using what tool? Solubility rules. Okay? So we need to know if chromium or hydroxide is listed in the solubility rules. If you don't know that this combination of elements is hydroxide, you can tell that there are 3 elements here. If there's more than 2 elements, then you're going to look on the common ions list and see if some part of the formula looks like a polyatomic ion. So here's the common ions list, and you start looking through here trying to find some part of this formula. So you go through all this, and whenever you do this carefully, you'll end up right there where OH looks like OH. Okay? So that's a hydroxide. Alright? Now that we know there's a polyatomic ion, we know it's an ionic compound. So using the solubility rules, then we can determine if it's going to be in water, aqueous, or solid. Okay? So chromium is not listed in here, but hydroxides are. It's right down here. Okay? And it says hydroxides are insoluble. Insoluble means that in water, they're not going to dissolve. Okay? So most hydroxides are insoluble. They're not going to dissolve unless the hydroxide is attached to a group 1 element. Well, group 1 are those elements in column 1 of the periodic table. And chromium is not in column 1, it's over here in the transition elements. Okay? So this is not a group 1 exception. Okay? It also says an exception would be hydroxide bonded with strontium. Well, it's not strontium or barium. So there's no exception for this hydroxide being insoluble. So it will be a solid. Even in water, it's going to be a solid. Does that make sense to everyone? All right? Not hearing anybody say no. Okay, let's go on to something else. Determine the physical state of this substance if it's in water.